Welcome everybody to the second day of January 2023 Hexa-X ICT-52 project joint workshop on 6G. So today our topic is architecture, and we will start very soon with such presentations. Please note that the session is recorded. So we could get gradually ready with the first speaker coming from Hexa-X project, so Mårten Ericson. Maybe Mårten, you could activate your camera.
Yes.
And already.
I hope you can see me or hear me. Yes.
Can hear you well, but not yet see.
Well, let's hope that works too. I can start sharing my slides. So I cannot see your your video either. Actually, it's completely blank. Can anyone see the slides?
Slides can be seen and you can be heard.
Yeah, that's the most important thing. So maybe you can. I can't see your video either. I don't know what happened really. But maybe we can manage with this anyway. Let me know if there is something strange. I start here.
Yes, so I don't know if you want to wait still a very short time as we are at the very beginning,
no problem.
And people are still joining.
We can do that. You decide.
Yeah. So very soon let's get going, but still allow people to come in. Also now it turned 2 minutes past the hour already, so we should also give a good timing for those who come in time. Yes, so once more, welcome to this second day of Hexa-X and ICT-52 project workshop on 6G. And as said this morning, the theme is architecture, and we have a set of excellent presentations starting with Hexa-X, and Mårten, the floor is yours.
Thank you. Thank you for that, Mikko. Yes, my name is Mårten Ericsson, and work package lead then for the architecture work package in Hexa-X. So we discussed the latest deliverable basically here. We have three main objectives and three different areas we usually talk about. So the first then is the intelligent networks, and then we have flexible networks, efficient networks, and these go a little bit overlapping sometimes, but it's good to, they also work together, so you cannot really maybe have one without the other ones. The intelligent network is of course then AI and programmability, the enablers for this. Flexible networks is then components to make the network for 6G even more flexible. And efficient networks then is to investigate means of streamlining, redesigning the architecture to get it more efficient. And then there is a figure here showing these different type of networks we have nowadays. The networks get more and more complex. We have satellite apps, and we have private networks, smart factories, and a lot of different verticals and so forth. So everything has to be cooperated, and that makes it more complex. And thus also is our background of this, why we're doing this. We want to make it more simple, more smoother, more flexible, and so forth. As I said, I will mostly discuss this one, the last deliverable. We also work on the last deliverable, 5.3. So, and it will just be a very short snapshot, but let's see if I hope I can get a little bit flavor what we're doing here. So this is then the intelligent network, and this figure is just to show the different enablers we have we're working on. This intelligent network, we have a lot of work here. So the enablers are then the blue boxes here, and this is a little bit 5G type of figure, but what we can see also here is important to know that we have this cloud continuum. We assume we have this cloud continuum, we call that we have cloud everywhere. In this case, we have cloud RAN and core network, but also the cloud could be even down to the UE, we say in some cases. We have a common analytics that the different enablers can use. especially the AI perhaps, but also network automation. Management also is going everywhere over this and orchestration. So I will talk then a bit mostly about analytics, AI, and a little bit automation. So fortunately, no time for the rest. So analytics, as I said, as it is today in 3DP, I think release 17, that there is this network data analytic function that is able to collect data and distribute data over the network. However, this is we need a little bit more generic solution that can work cross planes and cross domain. We talk. So as it is now, they are these different domains or planes. They are doing this collection themselves, and then the management can maybe distribute this. But we think that we need to have a better way to distribute the analytic, the data over this, or models also. So in these cases, this figure here shows then two different domains, and one RAN cloud and a central core cloud, and how they cooperate with each other to send information, the models, or there could be different trainings and so forth, and extending this network data analytic functions so it can work over the whole network. And this is about AI, and the different AI functions shown here. We also develop the needs for and investigate different needs of different functions that we need here. So that's also necessary. One of these is then orchestration, which I'll talk a little bit more about here. So an orchestration and management then to have the full network automation is one of the goals also we have. And maybe someone can mute. I can hear someone talk here. So please mute everyone. And the current solution then is that if you want to the management orchestration, that you have so-called embedded pre-trained algorithms, and of course you can change that over time as you fit, but it's a little bit cumbersome to do that. So AI is a perfect fit for this, but then there is a problem with AI where to put the AI functions instead, and how do they share information between each others. So once again, we have these two different domains, core cloud here and edge cloud. And the solution here is that we have to allow this hybrid solution. Is one of the we probably have to have that solution, so we can put the AI agents where the compute power is, because maybe sometimes the cloud node, the core cloud node, is not having compute power enough to do all the collections and compute of the AI functions by itself. So it has to push some of the functions. Here's the AI agent here to the edge node that works just on this edge node. But then there's another problem for that. You have to then inform the core node about this, the models you do, the findings you have. So then there is some arrows back then. So there you have to duplicate a little bit here, and you have to send the information back and forth. So this is we think this could be an efficient way to do full network automation. You have it very flexible, but the disadvantage is a little bit more overhead, but the benefits will be much higher, we think. So it's something we'll investigate further. Next step is then a little bit similar also here. They are, it's a little bit red thread here with these slides. These are different domains again. So here we have a figure with different circles, and each circle is a security domain in some way. And 3DP now there are ways already to communicate between different domains via this network exposure function. And basically you have two different trust levels. Your own network is trusted. The other is not trusted. So they are separated by this network exposure function. What we say here that we may continue this solution, but we fine tune it a little bit and make it much more granular, and the possibility to have not only untrust, we could have some different levels of trust. So this one is the first here. NEF1 is then super trust. It's your own car. We usually say here, your own car. NEF2 is maybe your neighboring cars in the highway. And NEF3 is a wider area, a city or whatever. And they can share some of your data. The NEF1 can share a little bit for NEF2 and even less than for NEF3 and so on. So the security level, you can share some, maybe it says here also very interesting, F3 here is this text here. You can access training data from secure data from 2 and very little from 1. So it's the opposite also holds here. So there's a way to make it the security and trust and sharing the different, yeah, here it's AI again, but it could be other type of exposure data in a secure way and a granular way. And this will also lower the overhead in the network. So let's go to a flexible network. Here we talk about ad hoc network and new multi-connectivity. We talk a little bit about satellites, and all these together should be this flexible network integration. Of course, there are other aspects also here, what we cannot really search on everything. But so I would give a short introduction to this mesh network and why we think this is necessary. So the reason we think this is necessary with the verticals, there will be a need for temporary networks that it could be a new sport activity, sport event, or it could be mining or whatever. Some vertical needs some capacity or high capacity, low latency, better coverage for a certain time. Then this infrastructure-less ad hoc mesh networks could be one solution. And it leverages then on D2D, as you see here in the figure. But it also employs every node in the area that is there and tries to do that, and devices. So it tries to discover all the nodes, and then it sorts them depending on the trust. Maybe you have a database on the trust, or maybe you have other ways to evaluate the trust. The untrusted goes away. And then when you have the trusted ones, you can select the best connections. And when that is done, you basically have your network, and you can then the network controller can put resources to the different users. And this is a lot of management, as you see down here. Also a little bit connected to the AI I talked about above. This is also a demo about this, so we see we will have some evaluation and demo of it. Multi-connectivity we talk a little bit about. We think that this is even more necessary now than we had in 5G. 5G we have the carrier aggregation and dual connectivity and so forth. One disadvantage we thought that we did have two solutions. It's not really very efficient to have two different solutions doing almost the same thing. So the idea is to combine this into one multi-connectivity for 6G. We think that's more efficient, and they should, of course, take the best from the both of them. So we get both very good reliability and flexibility. The uplink and downlink should be decoupled for better efficiency. And we have this concept about this is also a little bit studied in 3D people already, that you can set some connections inactive and activate them a little bit. So we think that could be further developed to have it really quickly. It's not very efficient to have the connections on all the time, so it's better to have them on off, turn them off when they are not really needed. Then we have some simulations and evaluations for satellites, something called 3D architecture here. This is this picture, which then you split the architecture drawn over the drone here and the satellite, the UAV. So some of the baseband is made in the UAV, and the rest is done in the satellite. So we have one work doing this 3D architecture, checking how optimal it is and what could be done in the UAV depending on the satellite. So there are simulations down there how to optimize this. A virtualized solution, we call this. Then we also done simulation to check if what is really needed in the satellite architecture. Do we need to have inter-satellite link hops so that the satellite talk another satellite to reach the gateway on ground. When it's over the ocean, maybe you cannot see the gateway. Yes, you need that. You need to have several hops between the satellite to reach full coverage. And then we also evaluate these different schemes, how to jump, and then find out that this could be done fairly simple. So here's a figure of the delay here for different satellite options. Going forward here, then we have the efficient networks. So here, as we said, this is about making the network more efficient. We also talk about service-based architecture here to evolve that, reduce complexity, faster signaling, and something called function elasticity, which goes hand in hand with service-based architecture a little bit. I will talk all about efficient signaling and function elasticity here. So start with this function elasticity. So the idea here is that we could be more flexible in terms that push the network functions onto different domains on different sites, as you can call it. You see 3 different domains here: central core, some regional edge, and then a local cell site is just a single site. So they can then you can run different network functions on these different nodes then, or domains is better to call it. This is the cloud continuum as usual. So some of these network functions logical to have on the higher layer, as we have them right now on authentication, registration, so forth. Mobility could maybe be done a little bit on the regional here, and some time-sensitive signal processing you could do in the lower regions here. So the idea is then to allow distributed network functions over the network of RAN on the core network. And also have to something we call distributed NAS here. You see this figure down here described in the document a bit more detailed. I will not go into details here. So, but this will allow also some way to. This is also a way to pave the way for maybe a more evolved service-based architecture. Finally, we have this. Well, maybe it's not the final slide, but anyway, we have this efficient signaling. We call it separation of concern of network functions, and maybe make as it is now. This the traditionally we build the networks is that we didn't really think about the separation concerns very much. We thought about the functionality in different nodes in the what functionality should be in the SMF, AMF, and so forth, and the functionality is then overlapping for these different nodes, and that was efficient when they have these hierarchical networks to build up in different networks. That was very efficient. It didn't really that was the way to do. But now when we have the cloud or continuum, it's maybe not that efficient to do that anymore, and it's more efficient perhaps to do the separation concerns. We talk that the network functions should be more independent and self-contained to make the signaling more efficient. So this is just a figure ideally what we could have then. One example, for example, if you had more independent functions, and this is still this 5G type of network. So anyway, that if you have them self-contained, you don't have to wait for the response. You can send the signaling directly, the target node here in Hanover, you can send directly to the different functionalities, and then you get responses. So you can save some time. So this is just the deal. Yeah, then you have to do what happens if the response is NAC here. Then yeah, you have to. There are some. We haven't really thought about everything. We have other ideas how to make the signaling more efficient also. But this is maybe what I have today. So summary is this then. We have made an AI as a service framework, or analytics framework. We also talk about federated learning a little bit. When the network of networks, we talked about satellites and these ad hoc networks. And this separation concern, efficient networks. We show solutions how to make the network more efficient. Basically, I think that's it. I think I will stop here. So time for a few questions. Thanks for me.
Thank you, Mårten. So for the questions, you can either use the chat, which is the recommended way, and if you want to also make audio questions, you could raise your hand in the upper part. There is reactions, and there you can raise your hand. Immediately, right away, there is actually now there is a first question in the chat.
Yeah, I can ask it in chat, so you can make it continue. Or do you want me to answer it right now? Or yes, yes. It's from Arthur. Has who is the AI as a service from? I think we mean it from both for the network. It's not clear. It's a good question. In here we use it for the AI. We use this for full automation, for network automation. So then it's for the network itself. But of course, it should be exposed outside the network for a third party also. But I didn't have any show that here so clearly. So, but both.
Anything additional, Mårten, you would like to say when
No.
looking towards the final deliverable?
Yeah,
from,
we continue
Hexa-X?
doing evaluating. We focus on more on evaluation. So try to invest. Yeah, we have also defined a certain type of KPIs also. I mentioned a little bit about that, and try to see if we fulfill these KPIs to improve the network and see if we can. So we're going in the same direction I showed here, but trying to do a little bit more concept driven and evaluations driven. So that's a last step for us in Hexa-X.
Okay. Yeah. Thanks again, Mårten. And maybe we then move forward. So as a theme for this morning, in addition to architecture more widely about network evolution, and moving towards this space, second presentation from Hexa-X, so by Bjoern Richerzhagen on special purpose functionalities. So Bjoern, the floor is yours.
Thank you, Mikko. I hope you can already see the slides.
Yes, and can
good.
hear you well.
That's perfect. Good morning also from my side. As Mikko said, I'm Bjoern Richerzhagen, leading the work package 7 in Hexa-X, working for Siemens in Germany. And in Hexa-X, we basically discuss special purpose functionalities in terms of enabling extreme experiences. And what that means, I would like to discuss in the next couple of minutes, and also show you what we contributed in that regard in our deliverable D7.2, which is also available on the Hexa-X website. So in case you're interested, go check that out. We will also have a bigger update in June when we are going to publish our final deliverables. So this presentation is giving you some insights into what we're working on also towards this final deliverable. So then let's get going. What's the scope of our work package? Mission and scope of work package 7 is to study enablers for some extreme experiences. We want to increase dependability on the 6G system, and we want to achieve sustainable coverage. And I'm going to detail what that means to us. And some of the enablers we see there are, for example, digital twins and novel HMIs that can help us to enable some of those use cases that we also discussed yesterday. Overall, the work package contributes to the expansion, as Mikko already mentioned, of the network into those new use cases and also into some new, potentially new value chains. As I said, the presentation will mostly focus on what we already published in D7.2, giving just some hints on what we're currently also working on towards the final deliverable. And besides the technical contributions, we also discuss a bit the relation to the KPIs and KVIs that we identified in Hexa-X. So maybe to answer first the question what we consider to be extreme experiences, let me show you the Hexa-X use cases again. I guess some of you already saw a similar figure yesterday. So what we did initially, we took those use case definitions we had in Hexa-X right from the start and identified two groups of use cases where we argue that there is need for very extreme requirements, a need to support certain applications that go beyond what is possible today. And we group those into two categories. On the one hand side, top left corner, the dependability in Industry 4.0, which for example includes aspects of telepresence, which also includes the aspect of digital twins being used for manufacturing, and which includes aspects such as cooperating mobile robots. And on the other hand, we have the second aspect of use cases, which is the sustainable coverage in IoT on the bottom right corner, where we focus more on being able to provide a service to a certain group of users or devices in a sustainable fashion. And this spans use cases such as the Earth monitor and autonomous supply chains, but also the use of 6G IoT networks for smart cities, and overall the theme of having more immersive smart cities when we talk also about twinning in that regards. So we started from that and then defined what we understand when we talk about dependability and sustainable coverage. And this is just, again, maybe for your reference, dependability for us is the ability to perform as and when required. So basically being able to fulfill the application's demands. And we also believe that the KPIs that we use to quantify dependability can serve as a good indicator towards one of the Hexa-X key values, which is trustworthiness. And when we talk about dependability, we basically take two perspectives. On the one hand side here on the right part of this figure, we want to increase dependability for some individual services that 6G is going to offer. So most notably, of course, communication, but also aspects such as positioning and sensing capabilities, or the AI as a service or communication as a service capabilities of the 6G network. So we want to increase dependability for those individual services. But on the other hand, we also have to ensure that end-to-end dependability needs to be tackled from the application's perspective. So we need to increase, or we need to maintain the productivity of the application, and we need to increase the resilience of the overall system by considering dependability from this end-to-end perspective. For sustainable coverage, this basically, as I already briefly hinted at, refers to the ambition to both target the spatial coverage of the network, but also inclusion, while explicitly considering sustainability aspects. And some thoughts we had in that regard relate to the balance between the cost that is associated with the generated some kind of insight. So for example, collecting data, calculating some AI algorithms or models on top, in comparison to the value that we can get out of that generated insight. So for example, in the smart city use case, if we monitor movement of people, if we monitor pollution data, for example, and we can use that data to alter or to affect people's behavior in a sense that they consume less resources, that they act more sustainable, this would have some value associated to it. And in order to utilize basically this trade-off between the cost of insight and the value of insight, we require flexibility, which we also see as one of the core values in Hexa-X here. Flexibility could relate to, let's say, reuse of components, could also relate to adaptation of the network or of the system to cater for different and new use cases in the future. Based on that definition now, I would like to show you some intermediate solutions based on what we published also in D7.2. Again, this will just be, let's say, a high-level overview. For more details, please reach out to us or have a look at the deliverable. So in D7.2, we focus on three topics to address special purpose functionality. First of all, means to be ultra flexible in terms of resource allocation, especially targeting challenging environments where we have mobile devices, maybe battery constrained devices, or devices with very special requirements in need of coverage. So this is the first area of contributions. For the second area, dependability in Industry 4.0 settings, we look into mechanisms and enablers that increase dependability, focusing on vertical scenarios, industrial scenarios. Here again, we also look into how we can support the respective applications by providing the required resources, even if the environment changes quite dynamically. And last but not least, the third area of contributions deals with HMIs and digital twins. This addresses also this vision of Hexa-X to bring together the biological, digital, and physical world, or the human, digital, and physical world, through some novel HMI concepts, and also by providing an execution environment for digital twins that is able to, or that is privacy preserving, again, trying to address this value of trustworthiness. Now we can go through those one by one, basically, as I said, providing some highlights on what has been done. So for the ultra-flexible resource allocation, we distinguish between the network enablers on the left-hand side and the applications being in focus. For the network enablers, some contributions out of the deliverable would include models for in-machine communication, so addressing this network-in-network topic within factories, also dealing with frequency, the spectrum management, and so on. The second contribution in that regard that both addresses dependability but also sustainability would be the flexible functional split adaptation in factories. So trying to adapt the functional split that is being utilized in the RAN to the demands and requirements of the environment, and also being able to do that flexibly. And last but not least, targeting the sustainable coverage from network perspective to support zero energy devices, for example, for tracking applications. From the application perspective, we look into how we can map the radio environment in dynamic environments, and also how we can use that information then to plan trajectories of, for example, AGVs. We use flexibility in the sense to redistribute functions and resources in factories. This also relates a bit to the split adaptation that I showed earlier. And we looked into how we can provision resources for federated learning tasks on resource constrained devices or in an IoT environment. Regarding dependability in Industry 4.0, one thing that we focus on, or one important enabler that we need to tackle, is to understand and model the impact of the real-world constraints on applications. So this is where the term COCO comes into play, which refers to communication, computation, control, co-design, basically meaning that we study the impact of application of network behavior, for example, packet losses or mobility on the application, and try to design in a more cross-layer fashion the application such that the application can cope, for example, with certain packet loss characteristics over time. So we did some studies on that, for example, studying how the temporal correlation of packets has an impact on the productivity of the industrial control applications. We also did some modeling on well-known problems from control theory. So, for example, the inverted pendulum to study this approach. And we looked onto EMF exposure in offloading scenarios. So this is also something you can find in far more detail in the deliverable. We did that both from a theoretical perspective, so modeling, but also using prototypes, for example, with AGVs to study the real-world behavior of the models. This is not all that we did regarding dependability. We also have some contributions dealing with the quantification and later on also monitoring of dependability. One sub-aspect here being the identification of errors. So to really understand what is going on in the network and how that impacts the application at a later point. For this, we propose some architecture and also show a demonstration on how we can capture application, network, and infrastructure events that are relevant to do this error identification. And we use that data to estimate the impact on the application productivity, which again refers to what I presented on the previous slide, so this COCO approach. We also showed a demo at last year's EUCNC already, where we used resource allocation then to mitigate or to implement strategies that enable us to mitigate some failures in the network or in the system. So this is also work that spans multiple tasks in our work package. And as a bridge to the digital twins and HMIs, we can, of course, also use the information we have in the digital twins to increase dependability. One example here being, again, being able to plan trajectories based on the expected signal quality or network quality across the path that we want to use, and use that information then to alter the path in a way that later on provides some kind of guarantees for the expected quality of service along the path. Coming to the third area, the HMIs and digital twins, we looked into this ecosystem of digital twins. So we argued that you have multiple twins of different aspects of a system. For example, as shown in this figure, you could have an industrial digital twin that just copies or twins aspects of the real-world machinery of some kind of local network infrastructure that is being used and of the Industry 4.0 application that controls the machine. And this let's say, limited view is then augmented with additional digital twins, for example, from the 6G system that provides more information on or more capabilities in terms of sensing, in terms of localization, provides means to interact with the digital twin via novel HMIs. So you can see some examples also in the pictures below. Or just provides more network awareness. So extending the view of the digital twin from this local network, factory network, for example, to a more complete view of the overall 6G network. One study here would be on the impact of human presence on industrial networks, so on industrial wireless networks. So if people walk across the factory floor, how does that affect the quality of service that can be achieved? And of course, the capabilities that 6G offers. So compute or AI as a service is something that can also be used in a collaborative fashion among those digital twins, most notably to basically analyze more data also out of the industrial digital twin using the AI capabilities of the system. And based on those contributions, also in D7.2 already, we started to try to relate the contributions to the KPIs that have been identified in the project and have been published in D1.3. Again, the KPI areas being sustainability, trustworthiness, inclusiveness, and flexibility, or inclusion and flexibility. This is just to be considered a first step, so something we are still working on to also get more insights into how we can later on quantify the respective KPI areas based on the technical contributions we have in the project. So what you see here, and this table is also included in the deliverable, would be a mapping of the respective contribution to basically our thinking of the respective contribution in terms of how that affects the respective KPI area. And as I said, this is something we are still working on. If you want to know more about the works, I already mentioned that multiple times, we have the D7.2 already out there, so you can have a look at the deliverable. Of course, you can also reach out to us, but I guess more interestingly, we will have the final results, updates on all of those topics available in June on the Hexa-X website, which will be the final deliverable also of our work package D7.3. And with that, I hope I made it in time so that we can maybe have a couple of minutes also for questions. So thanks a lot for your attention and looking forward to the discussion.
Yeah, thank you, Bjoern. And there is in the chat, there is already a first question. So maybe you can talk about that.
Yeah, just have to read it. Just give me a second. So while your definition of dependability is a systemic property definition, you call it a KPI, which assumes a way of straightforward assessment. So how and what exactly do you plan to measure here, which was the question. So thanks a lot for that question. I guess this slide gave a little bit the wrong impression on that aspect. So we have for dependability different KPIs that we assess. So it's not that we have dependability as one KPI. At least from work package 7 perspective, we see dependability more as input to this key value of trustworthiness, as I said. And to quantify dependability, we have to then measure, for example, reliability, availability, and so on. So the different attributes that you would assess to dependability. So I hope that somehow answers the question. Again, for more details for the individual contributions, we have also more details on how they are assessed in the end.
Yeah, Arthur is continuing the interaction with the next comment on your reply.
You mean availability and so on. Mm-hmm.
Arthur is saying in the chat that these are just as well systemic properties.
Yeah, I see. Mm-hmm. Yeah, maybe this could be a definition issue that we might have to discuss offline, to be honest. Maybe I did not fully get the intention of the question on that. So maybe we can take that offline if it's okay for you. You could just reach out to me so we can clarify that.
Yeah, thank you, Mårten.
Bjoern,
anything?
Right? Not Mårten. You said Mårten. Yeah, but it's Bjoern.
Yes.
Yeah,
sorry.
I take the credit also.
Yeah, you also deserve credit as well as Bjoern. So, Bjoern, anything more to add on the final actions towards this last half a year of Hexa-X?
I just saw that there is another question. Maybe if you have a minute, Mikko, if it's okay
Yes.
for you, we can also take that. So the question was, where are these digital twins stored in the network of factory equipments? So maybe this refers to this figure. So the idea is that you basically have different places where twins are stored depending on the scope of the twin. So the industrial digital twin would be something we store on the factory premises. And the 6G digital twin would be something to be stored by network infrastructure, network equipment. And the idea is then that those twins can collaborate, so they do not need to be stored at the same physical place. This is basically the concept here. And regarding the way forward towards the end of Hexa-X, we're also working on, as I said, finishing the contributions, getting also more insights into how they can contribute towards quantifying the KPIs. And also, as I mentioned, the demo we had at EOC&C last year, this is also something where we will have an update, basically showing the full functionality as promised. So this is something maybe also to look forward to.
Yeah, thanks again, Bjoern, and Work Package 7. So then we could move forward to another European project, DEDICAT 6G, and hear from Francois Carrez, please.
Do you see my screen? Hello.
Yes, can hear you and can see the screen.
Excellent.
The slide.
So I just do now this and this, right? So hello everyone. I'm Francois Carrez from University of Surrey, a 6G Innovation Center in Guildford, Surrey. So I'm giving you a guided tour to the architecture of the DEDICAT 6G. It's a big document, so it should take a lot of time, but now it will be 15 minutes only. So I will try to be as clear as possible, and you can ask questions at the end, of course. So as far as the technical work is concerned in DEDICAT 6G, we have actually three main pillars, which are dynamic distribution of intelligence, which in that case means roughly taking care of functional component from the platform and any kind of microservice provided by a vertical, for instance, and making sure they are executed in a proper way with a minimal consumption of energy. So energy consumption is very important here. Second pillar is dynamic coverage, which is extending an existing RAN with some additional mobile access points, which can be terrestrial or aerial, as you will see. And the third one, which I will not talk too much about today, is about end-to-end enhanced security, privacy, and trust. I will just make a reference to trust at some point during the talk. Here you see schematics of the different use cases we are using to demonstrate these different technical achievements, and it will be detailed actually this afternoon by a presentation by Airbus. So I'm not going to go into detail of this use case. I will just use one as a red thread, let's say, during the presentation. Use case for coverage extension and intelligence distribution. The kind of scenario we have is typically an explicit request from a vertical for network extension. For instance, if you want to implement a music concert and you envision a large audience, you need to ask for more capacity from the radio point of view, especially if you want to provide high-end video broadcasting, for instance, which is the case of use case 2 for that. Another case is network optimization or equipment failure, where you will need to deploy some additional mobile access points and extend coverage. For dynamic intelligence distribution, it can be seen as a complement to the coverage extension as a service, which I didn't say here, but okay. And it can be also part of intelligence distribution as a service request from a vertical where you don't explicitly need coverage extension, but you still ask your mobile operator to deal with, with this intelligent distribution thing. Especially if you're a small business and you don't own any special server, you will rely on equipment provided by the operator in that case. For the real life scenario, you have social event, natural disaster, which is something very important, especially when using drones, when an area is not available for cars, for instance, and you want to maintain some coverage for the response team, let's say. You can use drones. Drones are mostly not used for other scenarios involving crowds for obvious reasons, but you can use other vessels for that. Again, you have a lot of more detail this afternoon. The coverage extension itself is based on the use of UAVs and MTVs, so some aerial, some terrestrial, some unmanned, and some manned. Okay, so we have used in the project drones, robots for the terrestrial part, a connected car also, and a swarm of drones, which have the capability to self-organize spatially, I mean. And as far as the coverage itself is concerned, it's based on IAB concepts, which is integrated access and backhaul. You can see more detail, a lot of detail actually on IAB, either going through the standard, which is 38401, or you go through an Ericsson paper online, which is very good introduction. So you will heard about IAB quite more in this talk. So from the general principle is based on this kind of loop, which is quite classical. So first we start sensing. So you are using agents scattered everywhere in the system. Some are focusing on edge nodes, some are on microservice and functional component execution. Some are more focused on the mobile access points, user equipment, or the network itself. And these agents are providing a lot of information to the second layer, which is awareness, which is building up context. So you have as many sort of context as you have agents here. Then you take some decisions depending on what you have to decide about. So it can be coverage extension or network optimization or etc. or just coverage extension. And then you rely on other components to act, which means to implement your decisions. So we have 4 classes of components which are used in the architecture. But besides this loop, we are providing SLA enforcement, because when you are going through coverage extensions as a service or ID as a service, you also obviously go through some SLAs, and you need to enforce these SLAs. So that's where actually trust is important. And okay, you have also these 2 mechanisms, which I'm going into detail more in the following slides. So to go through all picture, here you have everything about context building. So you have different sort of context awareness components. Sorry, I'm not going to go through all arrows, but you can go to the slide offline. You have also one agent which is deployed at the 5G system side to talk with the network exposure function. You have a network analytics, data analytics function talking with the network optimizer, and all these components are talking together. So optimization recommendation goes to the network operation decision making. Everything about edge nodes and functional component goes to the IDDM, which is so intelligent distribution decision making, and you have finally the coverage extension decision making, which is actually deciding about how to make a coverage extension depending on the requirements. And all these 3 components are talking with each other and cooperating. Okay. Coverage extension relies on a certain number of set of components which are specialized per type of mobile access points. So we have the AGVs, we have the swarm operation in case you have more than one drone, or just one single drone, or connected cars, and you have an additional one to rule them all, which is the map operation. The map operation is also responsible for setting up a network slice, which would be dedicated to a service request in case of coverage extension as a service, for instance. You come up with some requirement in terms of quality of service. You provide then some SLAs, and this map operation here will be responsible for creating a network slice using the service orchestrator. The service orchestrator itself is the one component which is implementing a task allocation plan, which is the purpose of intelligent distribution. And it relies on edge orchestrator and load balancing, which are again scattered in the different edge nodes at the far edge of the system. In addition to this, we have several components here which are providing a certain number of registries, description of microservice and functional component requirement in terms of execution, the edge nodes capabilities, how much RAM, how many cores, how many GPUs, etc. All of this is described here. SLA repositories, which is also responsible for enforcing SLAs, and edge computing policies, yes, which are describing policies for deployment. So which means that this component here, which is responsible for coming up with a deployment plan for all the component and microservices, can be constrained also by fixed policies. And this is particularly the case for the deployment of all components which belongs to the platform and not belonging to the vertical. So that's the whole idea of the architecture here. And obviously here for the slicing part, we are talking with SDN, so software-defined networks, controllers, and NFVs, which is network function virtualization. So that's where the creation of a slice is done. And the creation of the slice, I mean, the lifespan of the slice will depend on how long your service is going to run if you go through a coverage extension as a service. So it can be for 2 days if a concert, for instance, is lasting 2 days. All right, this is an example of deployment. That's time flies, so I have to be quick. So here, service orchestrator deploys, in the case of the second use case, we have different microservices, video streaming, video transcoder, and multicast unicast platform. So they are deployed by service orchestrator, which is also deploying the needed components. So in a physical system, which is roughly an edge nodes, you need to deploy microservices, and you need to deploy components which are provided by DEDICAT 6G for the execution of this, for the monitoring, let's say, of the execution of the microservices, which is the monitoring is part here, and here to rebalance the load of the different execution environment, which are part of one edge node. Obviously, you can have more than one edge node. Okay, and the other aspect is here the deployment of network function in the mobile access point. So in that case, we have by default the IAB distributed unit, and we have the IAB mobile termination components, which are needed for the IAB concept to work and to make the network extension. Okay, so this one I probably can skip it, so we can go through the slide offline. Yeah. There are scenarios. I mean, this one is a scenario which explains roughly what happens when you take the decision of migrating one component from one execution environment of one edge node to another execution environment of a secondary node, because let's say the execution as it is detected here and here doesn't fit the requirement of the component. So in that case, you decide another task allocation plan, which is done by the IDDM, and you instruct the service orchestrator to just move one component from one edge node to another. So there are this one and the previous ones are some detail on how it works. Here, for instance, you have a status agent which is doing aggregation of other status agents in the same edge node and provide information to the corresponding awareness component. Yeah, there's a lot of components in this architecture, so it's not necessarily easy to follow. As far as architecture is concerned, we are exactly in the middle of the work. So we have two documents out of 3 which are ready. So if you want to read this document, which is something like 160 pages, you need to download D2.4 V2, which is available on the website. It follows a precise methodology, which is based on Skinwood. Again, you can Google this and have a look of what it means. We have different views and perspective as defined by this methodology. And content-wise, let's say we have a complete functional decomposition. So we have 40 and some pages of description of components. We have an information view, which is providing data structures and interface for all these components, which is also 40 and something pages. We have deployment diagrams, which are either generic or relating to one use case in particular. So we have 5 in total in the document. And you have a comprehensive set of system use case. I will tell you what it is. System use case, so I'm not going through all of this, but there are more shown as an example. We refer here to the precise API. So going through the information view, you can really see what it means to do this, and this, etc. So this one is about setting up coverage extension as a service. This one is more complex. It's the whole process of coverage extension, decision making, and what it means in terms of deployment of components. All of that. Here you have, typically you can't read, but I'll tell you what is here. It's the setup of slice and the configuration of mobile access point, which is actually this sequence diagram here, where you are asking the map operation to execute a plan, which itself asks service orchestrator to implement a IDDM plan, etc. You deploy the DU and the MT component from the IAB to the mobile access point, which you are then deploying, etc., etc. You go here through the slice creation, and then you are ready for activation. All right, so it's a bit fast, but it's a bit complex also. This last one is a complete view of the architecture in the 3GPP style. So here you have the few components which are interacting with the 5G core, especially with some of component here and here, and also with some Mano components, which are the SDN controllers. So there are more than one usually, and NFV orchestrators, which are also more than one. And RR is a component which provides information on existing slice. So here you have a description of how it interacts, which kind of interface is involved, and you can refer to this keywords here and go to the information view to see what it means. And here, at the bottom of this picture, you have the 5G RAN, which is extended with IAB. So here you have 2 GNOT-Bs, which are classical GNOT-Bs. And this one has been extended with IAB donor capability. This IAB donor is talking with IAB nodes. So here you have 2 scenarios. One is a single hop, where the IAB donor talks with the IAB MT of each of the drones, because this ones are drones. So you have 4 red lines here going to the MTs. So in that case, UE will talk with one hop to the IAB node, drone, for instance, and then the drone to the IAB donor, which is a GNOT-B. Or you can go through multiple hops going through an intermediate nodes. In that case, it's a connected car, which is then serving the IAB MT of each drone from the IAB DU of the connected car itself. So that's how multi-hop coverage extension can be done. For multi or single hop can be done using mobile access point. Okay, I think I'm just done here. Sorry, it was very quick. So if you have any question.
Thank you, Francois. There is no immediate new question to you in the chat, and as one of the parts of the scope of your project is to address the connectivity for remote areas.
Yeah, exactly. That's exactly where you are using these drones or connected car, which you can deploy nearby GNOT-B. That's the idea. Yeah.
Yeah, and for these remote areas, with the approaches that you have, when does it work for the remote areas? What kind of constraints there are, and any other comments if you have on how do you see the spread of connectivity to remote areas?
Okay, I think the main problem here would be the backhaul link between a node and the donor. As far as I know, in 5G, you have two range of frequency. You have FR1 and FR2. FR2 is millimeter, and FR1 is a sub 6 gigahertz, I think. So if you want, and the micro, the millimeter wave, you have obviously a higher throughput, but little coverage. So you would have to have anywhere nearby the remote area. You would need a G0B anyway if you want to have a proper coverage using millimeter as backhaul. So, but if you just want to provide a standard 5G backhauling, of course you still need a G0B anyway. There's no mystery. You need a G0B somewhere, even for remote areas. But you can improve the coverage from villages, for instance, putting an intermediate relay. So you would provide two hops, let's say coverage to remote areas. But anyway, whatever you want to do, you need a G0B somewhere. I think it's pretty reasonable. The coverage extension we are doing is through radio, so that's why. So I don't know if it answers your question.
Yes, it does.
Yeah. Actually, I had this problem. Yeah, I have a house in France. It's a small village, and because of some shadowing problem with a hill, my house is badly covered, and some rest of the village are covered properly. So just for me, it would be nice actually to have a relay, somewhere at the entrance of the village to provide us two-hop connectivity. So that kind of scenario is pretty happening pretty often in the countryside, I'd say.
Yeah, it does answer like of your solution and its relation. It does not yet answer the more generic question, but I don't know if you have something more to add on how do you see this remote connectivity in general? Anything more to add there? Or?
Well, for remote areas, I think I don't have anything to add. But if you take scenarios like natural disasters, etc., I think Dražen Rybar is going to talk more about this this afternoon. But typically, they come up with a connected car with a lot of radio capabilities, even satellite, for response, for the response team to work properly in a disaster, a place touched by disaster, like a earthquake, for instance. But again, I mean, using either a airship or a drone, it would work ultimately in our solution if you have a G0B nearby, which is properly working. In the case of natural disaster, if it doesn't work with 5G in that case, it would work with a satellite probably, or even with other fancy radio methods. But again, I think you will get more detail, or you can ask more detail.
Yeah, once more, thank you, Francois. Yeah. And then I would propose that we move forward in the agenda.
Sure.
And here then the latest updates from Samsung and Dan Warren, please.
Hi there. Thank you, Mikko. Hopefully my slides are about to appear.
It was visible, but actually not anymore. You can be heard well.
Let's try again. How's that? You see now?
Yes.
Okay, good stuff. Okay, so thank you very much for the invite. And obviously, because it's a presentation by me as Samsung rather than from a project, it's a little bit different in style. So it's more forward-looking than talking about things which have already happened so much. So no discussion of deliverables, more looking towards changes in architecture that we're going to try and work on generally in research, but I will point out where we're going to bring some of this into particularly SNSJU projects and also some UK government funding that we've received in a collaboration led by University of Bristol. So I've titled this Beyond SBA mainly because I personally have this itch that I've been trying to scratch for a number of years, in that the architecture in the core in particular hasn't changed a great deal really for data since GPRS. So the acronyms change, but the functionality remains pretty much the same and clustered in much the same way. And when you look at the direction we've taken with SBA as a whole, we're now in a position where the network functionality is completely separated from hardware. It kind of was heading that way in EPC, but now we have an SBA-based architecture that's fully embraced, and the hardware to a certain extent is not completely forgotten, but the hardware can reside anywhere, and the network topology is very flexible and very open, and that makes me wonder whether maintaining the AMF, which, for example, which if you look at the lineage of the AMF, it goes right the way back to a 2G GPRS SGSN. So yeah, we're at a position where perhaps we can start to do things differently, and what we're starting to look at within Samsung is methodology whereby we could do that. So within Samsung, we produced a 6G vision paper, and within that there was a number of I guess big topics which are identified, and some of these slides draw on that. So I don't think there's anything here which is particularly unfamiliar, but where we're heading towards with the 6G network is much greater levels of intelligence, and a whole new divergent ecosystem of devices. And for today in particular, what we're looking at for networks and software is next generation communications, which have embedded at the beginning security and privacy, but also have this idea of an intelligent software platform. So, many of the presentations this morning, and additionally a lot of the work which has taken place at the back end of 5G PPP and within projects in the first phase of SNSJU, is all looking at how networks are orchestrated, how lifecycle management can be leveraged fully, and all of that is enabled by having this idea of an intelligent software platform. All of that, in my opinion, fits under this view of next generation communications. So to look at what underpins that, there are two mega trends, and again, this isn't my terminology, this is quite corporate. The two mega trends which I'd like to identify for today, AI and ML, which again we've heard a lot about both today and also in the presentations yesterday afternoon. There was a lot of discussion of how AI can be brought to bear to essentially optimize the network around differing KPIs or differing restraints to make sure that we have absolutely the maximum performance out of the network without having to throw vast quantities of capex and opex at the situation, but at the same time embracing the use cases which are coming from verticals, which have perhaps more stringent KPIs, certainly more challenging KPIs than human users do when we start to look at requirements for machines, and that overall is driving a lot of the requirements which we're seeing come through for 6G. So it's very difficult to hit some of these extreme KPIs in a network which is easily deployable at a reasonable level of capex and opex without implementing AI to offset some of those more challenging requirements that have got to be met. So when it comes to the parts which implement that, you need to look at things like coverage and KPI prediction. You need to look at monitoring and the prediction of interference or challenges which you might experience on the radio, and look at the root cause analysis of that, and then combine all of that in the middle around balancing load, making sure that you're supporting all of the network slices, orchestrating the right network functions in the right places at the right time, and perhaps more interestingly from the perspective of orchestration, removing functionality when it's not being used, or taking slices out of service when they're not needed by any particular service. So that whole idea of employing AI across the end-to-end architecture is one major trend. Then the second one, which I've kind of hinted at already, is the direction of softwarization and what that enables in virtualization and implementation in cloud. And again, a lot of what's on this slide, we've seen come through in the architecture white papers that have been produced by the architecture working group in 5G PPP, and we see that reflected also in documents like the SRAA, the SNS Call 1 and the SNS Call 2, which was launched in the last couple of days. So, as we move towards that virtualization of, on one side, the core, and all of those functions which are identified there as cloud native network functions existing in a relatively software-based implementation with a little bit of kind of database sitting above that for management of not just subscribers but also dynamic state, then all of that becomes topologically highly flexible, and we start to look at how the orchestration that sits above that can be, I guess, unified at some level and also made to operate in a way which is hands-off and be able to optimize the resource utilization within the network as smoothly and efficiently as possible. On the RAN, there's trends around topics like Open RAN, but the virtualization of the RAN is something that's been ongoing for quite a while. The separation of CUDU and RU allows us to look in the direction of perhaps moving some of those components more towards the core network-based implementation. So certainly the CU control plane function looks more and more like it's realistically an element that could be consolidated into the core, particularly when the core also is moving in some use cases towards the edge. So having a logical and physical separation between CUCP and core network elements in MEC makes less and less sense when essentially they're all sitting on servers which perhaps are not running at 100% capacity. So consolidation there and the potential optimization of that is one trend. And then as you do that, you start to look at, well, are there topics around user plane commonality, and perhaps even moving the DU and the interface between the DU and the CU control plane elements towards an SBI. So that then asks the question of, well, what do you need to do to achieve that? And the research challenges or the research areas that we've identified fall into three categories. So AI applications at the top are places where we've done considerable research already, and we're seeing AI applied on a per function, a per domain, or an end-to-end basis. And again, there's strong evidence of that coming through also from 5G PPP projects, and we've heard about that through the last day and a half as well. The end-to-end part actually requires quite a lot of understanding. If you're going to do full end-to-end optimization of AI using AI, you need to be taking into account all of the AI that's operating in a per function, per domain model, and then consolidate that and deal with any conflicts which need to be taken into account. So optimizing against one set of KPIs in the RAN and another set of KPIs in the core potentially creates conflicts. There's also questions about the correct order in which the different AI applications are implemented, and the prioritization of one AI application over another when it comes to per function or per domain implementation. So that idea of an end-to-end optimization using AI has to take into account all of the AI in the individual domains. That then leads us in the direction of AI enablement. So data exposure is a fundamental requirement, commonality in the approach taken to how data is exposed from the network. Again, has existed in networks for quite a while. Topics like NWDAF, MDAS, some of the directions coming from ORAN around exposure of data to near and non-real-time RICs all fall into that category of standardizing how data is formatted and how it's exposed. What you do with that then means that you need some form of AI layer sitting with or above the network where all of that data gets consolidated, and that needs to be something which is either controlling all of the AI which is taking place within the network, or is at least cognizant of where the AI is and can have the results and the intent of those AI applications communicated towards it, and then orchestrate the AI itself back down in ways that make sense for the overall operation of the network. And that that last one of interfaces for actions is a place where we're kind of lacking at the moment. So a lot of the application of AI is embedded within network functions where an interface isn't required. But when it actually boils down to taking action on an end-to-end system, we need to have the AI architecture with well-defined interfaces towards orchestration and management layers to enable the actions which are recommended to be implemented directly. On the green side, optimizable network, we need to, we have some level of optimization within the network, but if we don't change the way the network is implemented, then all of the value of AI is going to be lost. So again, topics which have been covered already, core and management beyond SBA, compute and communication convergence, and the core and RAN are actually all enablers of the optimization of the network as a whole. As we stand at the moment, the existing architecture of the network doesn't allow us to optimize fully, and certainly doesn't allow us to achieve full end-to-end efficiency of resource implementation and utilization. The reason this is a Venn diagram is because while these three topics are discrete, there's places where they cross over. So we're aiming at the end-to-end optimization of the overall system performance and operation. This is kind of a nutshell 6G goal where it kind of takes into account doing more with less, a bit around network resilience, a lot around the full utilization of resource to make sure that we're running an efficient network. But it's kind of trying to say that a 6G network needs to have a level of affordability to make the business case for 6G applications to fly. We can't target just that top line statement in the middle individually, so we need to look at the places where the different domains cross over. And so a common data layer for exposure and an AI framework which enables that network AI layer is an interesting challenge. AI for lifecycle management and MANO is where that end-to-end optimization of the network takes place. The optimization of the AI itself, and that can be both around things like tree pruning, but also the implementation of federated learning, and as a result, split computing. And then finally, we need to have some standards for data exposure and actions, and we also need to very much move towards all forms of state as data points, which are then able to be offloaded from individual network functions to allow a fully stateless architecture. What all that does is increase utilization of server resources, reduce the total number of servers required, which lowers CapEx, lowers OpEx. And it means that then the network is a lot more adaptable, easy to reconfigure, easy to implement new services. So it's all driving towards a much more flexible network where you can do more with the resources that you have, rather than having to just throw resources at the problems which we're going to run up against as we move beyond 5G and in towards 6G. To achieve that goal, we've got a shopping list there. So where we are now is SBA with NWDAF, MDAS, and NEF for exposure of data networks. We're moving further and further in the direction of RAN disaggregation and open RAN. We have network slicing. We have an edge and cloud-based implementation, and we're at the beginnings of the introduction of AI. Where we want to go is to have fully native AI and comprehensive AI, programmable 6G system, all the things that we've been talking about: communications, compute, convergence, edge cloud continuum, split computing, and so on and so forth. And then these are the research topics that we're aiming at to get there. And again, it's a restatement of what's in that Venn diagram. So this is how we evolve from one to the other. And then I wanted to dive into two specific areas. So this unified data layer requires a kind of a consolidation around some of the functionality that exists already in definition of near real-time and non-real-time RIC, NWDAF, and MDAS. These need to be kind of working in concert to expose data into a common domain. Where we're going at the moment is an implementation of silos. So if you look at the architectures defined in O-RAN Alliance and in 3GPP, we have a kind of a hierarchical structure of what data is exposed where, and it falls roughly into a RAN and core domain split. The UE sits kind of outside of all of this, and its data which is being exposed is shared across the two domains. if we want to have genuine end-to-end AI implementation, we need some level of unified data, because optimization end-to-end requires full visibility of the data that's going to be used as the basis of that optimization. And then we need the AI domain to exist in a common space. So the idea that we have domain-specific AI in the form of either AI applications for the core or XApp and RApp is fine. The organization of all of this AI into a hierarchical model which allows, as I was talking about, conflicts to be mitigated, AI to be implemented in the correct order to gain overall implementation, and for interfaces to exist back down into the different domains and different network functions to ensure that the recommendations put forward by the implementation of AI are carried out in the network is still a fundamental challenge in terms of standards and research. And then when it comes to going beyond SBA, we still have this model of 5G network functions, and we need to kind of get rid of those and look just at the services as they're defined in 3GPP right now. So as things stand in 23501, 23502, and then some of the specifications that extend beyond that for topics like policy and security, and then also for management layer as well, we still have collections of services in network functions, even though the services are all software based. And the reality is that all of those network services can actually exist in a highly flexible domain. And one of the challenges which we're starting to look at in terms of a network architecture going beyond 5G is what is the right way to organize those network services. It doesn't have to be tethered to the existing NF definitions anymore. Those NFs, like I say, are kind of historic, somewhat legacy, and because of that, they're tied to a pre-existing set of topological assumptions, which don't necessarily apply in a cloud-based or software-based implementation. So I think that was my last slide. There's a couple of white papers here where Samsung's laid out our view of where we expect 6G to go. Probably the 6G white paper published first in 2020, but there's further versions of it which have been published since and are all available on that website. But then also looking at 6G spectrum and laying out requirement for a spectrum strategy, particularly with an eye towards World Radio Congress 2023. They're both available for people to download if you're interested. But when it comes to architectural aspects, we'll be working on these things within Imagine 5G, Verge, and then also going on to the Reason project within the UK. A lot of that is focused around AI, but there'll be aspects of the evolution of core architecture beyond SBA filtering into those as well. And with that, I think I'm probably done. Thanks.
Thank you, Dan. You have 2 questions in the chat, and maybe you can work on them offline or address some of that right away.
Yeah, so Arthur's question on the relationship with resources. Yeah, so one of the other challenges I think, which I didn't draw out explicitly there, but is challenge around orchestration. So where we've got to now, we have a service orchestration layer, we have a network function virtualization orchestration layer, and we also have a container orchestration layer. And that seems like too many. So I can kind of see Arthur's point about this isn't addressed in SA2. The fact that these things aren't addressed in SA2, I think, is one of the fundamental problems, that the SA2 view doesn't take into account resources underpinning requirements for network functionality. The challenge, though, is that as we move towards 6G, we're seeing requirements coming through, particularly around things like energy efficiency. And energy efficiency has nothing to do with software. Energy efficiency is about underlying resource. So we're going to have to address underlying resources in a far more fundamental way. And we're going to have to take requirements for energy efficiency seriously about how network functions or network functionality is applied on top of network resources in order to address energy efficiency as a whole. That, I think, means that the perspective of 3GPP will change. And then we're going to have to go into this in a way which means that the orchestration top to bottom through the stack is something which is consolidated and taken as a much more holistic overall requirement. And then for the question from George, possibly Jorge, depending upon which part of the world you're from, getting rid of VNFs, yes, possibly. One of the interesting things we're looking at the moment is whether VNFs NFs in general still make sense in the way that they're implemented. So the SBA architecture, as I say, could be viewed just as one huge software module. You could conceivably implement the entire core network within one container, internalize all of the SBA interfaces, remove a lot of signaling. That's probably too far to the opposite extreme. Equally, getting rid of NFs and exposing every individual service at kind of the 23502 level of granularity, that's probably too extreme the other way. But I do think there's a fundamental problem with network functions in that the way that they're clustered together means that you have multiple procedures running through, for example, an AMF. And whilst the AMF scales according to the highest required procedure at any given time, that means that there's an awful lot of resource being consumed by that AMF for procedures which aren't happening. So one of the things we're interested in is whether you can pivot NFs and look at the services in a slightly different way and orient them more towards procedures. There's been a couple of other academic papers, one I think by Nokia in particular, which have started to look at this as well. But we're taking a slightly more radical view of that and looking at how that clustering works best from the perspective of overall network orchestration.
Yeah, thanks again, Dan. I propose that we then stop for a break and continue according to the original schedule. So that would be 9 minutes from now. So thank you, and let's come back 25 minutes to the hour. Let's gradually get going again. So not yet exactly 25 minutes to the hour, but very soon. So Marco, maybe you could already start sharing your presentation so that you are ready to go.
Okay.
So we have a presentation from DAEMON European project. And now, at least to me, it is 25 minutes to the hour. So yes, happy to hear from the DAEMON project. Marco, please.
Hello, good morning. Can you see my slides?
Yes, can see the slide, can see you, and can hear you well.
Okay, perfect. So, good morning. My name is Marco Gramaglia. I'm a professor at UC3M, and I'm involved in the DAEMON project. So today, I'm going to talk about our work in the project about the architecture, and specifically the network intelligent plane for 6G networks. So this will be the outline of my presentation. First, I will introduce the concept of network intelligence in 6G, how we defined it in the project, and then I will go into the details of the NI native architecture that we are developing in the context of DAEMON. So let's start with the network intelligence and why network intelligence is fundamental for 6G network. So basically, it's because of the objectives that we have with 6G. So we want to have near zero latency, apparent infinite capacity, very, very high reliability and availability, and also having other soft KPIs that, for instance, allow the communication between the infrastructure and the service provider kind of transparent through the network. So meeting all of these requirements will basically increase even more the already high complexity that we are having for the management, orchestration, and operation of the 5G network. So clearly, the traditional human-in-the-loop approach that we are having nowadays will be not scalable anymore. So here we envision the role of network intelligence that we mean as the set of smart algorithms that we're going to deploy in 6G network, basically for two purposes, very high level in this case. First is the automated decision making. So we want our network to be autonomous in the decision making, but also adapting the resources and the network function to time varying demand. Of course, we have services that will not have a constant demand over time, and the performance requirement. All of these, as I said before, without the need for human intervention. So as in many other areas, we have artificial intelligence here as the candidate technology for providing network intelligence, because it is good to solve very complex tasks. And most importantly, we have a lot of data available in the network that can be used to train such artificial intelligent algorithms. So this data comes mostly from control plane, but we also have user plane data. So the challenges that we have to face here are basically two. First, we are seeing that legacy network management solutions were not designed to deal with AI. So standardization bodies are addressing these issues, but we need first to design an end-to-end NI native architecture that go beyond centralized orchestration. So we don't want to have NI that operate in a vacuum, and to provide this network intelligence directly at the network function. And then as a second iteration, we want to develop customized AI techniques that empower this practical NI. So in this presentation, we're going to focus on the first of the two problems. So if you want to have more information about how we developed custom AI techniques for the network operation, you can have a look at our website. So this is our proposal from DAEMON about network intelligence native architecture. And in order to do that, we first started with a diagnosis of the problem. Here, you can find a sketched description of a network architecture spanning different domains, both from the infrastructure perspective, so starting from the UID up to the core, and also for different domains of the network. So RAN, edge for computing, core network. So we have very different domains that all of them need to have this control loop, as you can see here, that allow the autonomous operation of the network. So here, we basically found two problems that we need to solve. First, we need to find a way from the architectural perspective to inject network intelligence within DNF, and find a way to remove this barrier where we have a different siloed control loop. Okay, this is because two centralized closed loop models at the end of the day hinder the effectiveness of AI. So if our control loops are too dedicated to a specific domain, we may lose the overall optimization of the network. So on the other hand, if we have two centralized solutions, we may have lengthy procedure that involve data gathering at the NF level, data processing, and the final distribution of the action. So as a result, they may not be affordable, and we need to remove this barrier between different network intelligence operating in different domains. So we wanted to unlock the full potential of NI, allowing the coordination of this intelligence, integrating this additional loop across network intelligence operating in different domains that need to provide NI management into a mobile network. So this network intelligence orchestration need to operate at different time scale, basically allowing the operation of intelligent targeting at the orchestrator level. So taking the decision that affects a large set of network function at non-real-time controllers when we don't have a lot of time critical functionalities, and we can allow a more scoped functionality. And finally, at real-time controllers, or either directly at the user plane, where we deploy the network intelligence in a very specialized and lightweight format. So this translates into a set of challenges that we have for introducing the NI nativeness in the system. So we may have limits and barriers in the way that we are monitoring the data, in the way that we are enforcing the data. As you can see here, if you want to have very high data sampling rate, then probably your data set could not be rich, because you are very targeted to gather that data very fast from a specific network function. And then when we are enforcing it into a decision making model, we have basically different operation points that trade off optimality for robustness, and the time scale of the decision. So for this cross-domain orchestration, we need to provide NI algorithm selection, so choosing the best NI algorithm for every specific task. NI instance coordination, so how to exchange information between different NI algorithms, and also having federated learning aspects that go beyond the traditional one. So we want to be able to exchange data among different NI instances to perform a specific operation. So here we define the concept of planes, new planes that we will need to have in a CC network. This concept were devised also with DAEMON contribution in the context of the architecture working group white paper that you can download from the website. And there basically we're discussing the concept of having additional security, intelligence, sensing, and network plane that are vertebrating the CC network. In this case, we are concentrating on the network intelligent plane and basically how we are leveraging it for network orchestration. So we do that by basically laying down algorithms using the MAKE framework that you have here. And it's basically a way of dissecting algorithms in standard component. You can see here that if the network is what we want to control, we have a loop that is involved: sensor, monitoring, analyze, plan, execute, and effector. So basically from the data gathering to the decision enforcement. And this is a common way of laying down intelligent algorithms. So using this structure, we can design our network intelligent orchestrator that, of course, may leverage learning algorithm like reinforcement learning one, but it can also use engineer models. So basically traditional control theory or MILP algorithm that can be used to control a network function, a controller, or an NFV orchestrator. So we devised a taxonomy for this. So following the MANO architecture, we designed a parallel ceiling architecture also for network intelligence. And there we define the concept of network intelligent function, that is basically an algorithm that is providing a specific contribution, like forecasting of load or configuration of an InnoD to provide some example. And this algorithm, network intelligent function, can be further split into atomic component, NIFTs, that are following the NMAK scheme that we presented before, and I will provide an example after. A set of network intelligence function is instead providing a network intelligence services that is basically a composition of network intelligence function that have a specific target that is usually related with the achievement of a target KPI. So you can see below in the table, if our network intelligence service is a reliable virtualized run, our KPI is the reliability, and we achieve that by the coordination of, for instance, two algorithms that we define in the DAEMON project. And basically, this is the same way that we use, for instance, for mobile broadband and different network functions that are built in the mobile broadband. And here we have the same for network intelligence. So going a bit deeper into details of our network intelligent orchestration framework, we have the NIF component manager that is basically the same, playing the same role as the Vim in a monostack. So basically handling lifecycle management of NIFs. The NIF manager that is handling the lifecycle management of a specific network intelligence function. And at the end of in the top of the hierarchy, the intelligent orchestration that is basically dealing of selecting the specific algorithm and coordinating the intelligence in the network. So an example of this solution based, for instance, on this algorithm that you can find in the reference, that is basically selecting, configuring a G-Node-B in order to achieve higher reliability. So basically, we can lay down inputs and outputs following our scheme that we defined before, and creating connection and specifying requirements, for instance, having a control loop or having a decision every 5 seconds at most. And basically, thanks to this definition, we can basically dissect network intelligent algorithm into specific components. So we are able to compose them to provide a network intelligence service as a whole. So as you can see here, we don't have a network intelligence that is orchestrated in a vacuum anymore, but it's directly integrated into the network. So this was a brief overview of how we are dealing with the network intelligence orchestration in the DAEMON project. Of course, if you are interested, you can find much more information in our project deliverable. So we designed the basic blocks and procedure and provided some example of the functionalities. And as a next step, we want to provide further details on the procedure. So how we achieve, for instance, coordination, this coordination or conflict resolution among different network intelligence instances, and also provide a proof of concept of our view. So this is the conclusion of my talk. So if you have any questions, just ask.
Thank you, Marco. Immediately in the chat, there is one question on the previous presentation, and at least not yet a new one for you. Maybe one question from me would be that, like, how do you see your approach with respect to some other activities, projects, proposers? How do you compare that one?
I mean, we are basically trying also to be compatible as much as possible with standardization work in the area, especially ORAN, ETSI, and also the work, the 3GPP-SA2 with NW, DAF, and all the analytics management that we have in the core. So through that portal, we believe that we'll be able to push our ideas in a consistent way, also with the ones that we have that are coming from other projects.
Yeah, thank you. Yeah, you had a conclusive presentation, so there were no further questions, at least so far, but great if you could also follow the chat for a moment to see if there are. So thanks again, Marco and DAEMON project, and then it would be time to move to MARSAL project. So John, the floor is yours.
Yes, hello everyone. Let me share my screen. don't know if you can see my screen.
Yes, can see the screen, slides yourself and hear you well.
Okay. Probably I will turn off the camera because I have some issues with the connection today. Good morning, everyone. I'm here to present the work under the project MARSAL. My name is Vardakas. I'm the coordinator of this project. And I will start by giving a brief introduction of the project and the main pillars of the work that is been defined under this project, and then I will focus on the work that has been implemented during the last period of 10 months. So you can see here in the figure the network architecture of MARSAL, which targets to propose a new paradigm of elastic virtual infrastructure that integrate targeting to integrate in a transparent manner a variety of resources, of radio resources, networking resources, network management and network security, targeting to deliver an end-to-end transfer, processing and storage services in an efficient and secured way. And in order to do that, we have defined from the beginning of the project, from the proposal stage, three pillars of innovation, let's say. The first pillar is related to the network design, to the definition of the sorry, something happened with my mouse. The first pillar, as I said, is related to the network design, where MARSAL pushes this self-free networking towards the distributed processing self-free concept, and also targeting to enable wireless millimeter wave solutions, which are implemented, and we are in the process of integrating with the existing RAN elements, while being in line with the Open RAN, with the RAN Alliance. And the second pillar is built on the elastic edge computing notion, targeting to optimize the MEC functionality and the network slicing management systems by considering a hierarchy of analytic and decision engines. And we have the third pillar, which is related to the network security, where we develop new innovative machine learning-based mechanisms target to guarantee privacy and security in multi-tenancy environments, targeting both end users and tenants. So regarding the architecture in the radio edge domain, we have, as I mentioned earlier, focus on the self-free approach. And we have two different solutions for the radio edge. The first solution is depicted in this picture, and it is based on this distributed processing self-free concept, where we are working on a novel self-free paradigm, where we disaggregate the classical self-free approach, and we disaggregate the CPU node into many DUs, and supporting distributed computation and coordination between the different access points or radio units and between the DUs. We are working on the development of clustering algorithms, where we consider clusters of access points or RUs that provide service to each user. And since there are cases that these clusters of access points may comprise of access points that belong to different DUs, we need inter-DU coordination. And all of this should, of course, be developed by considering the constraints of the front haul and the mid haul links, mainly in terms of the restricted capacity. The second solution is based on, and as we call it, the hybrid MIMO front hauling solution. We consider large massive MIMO antennas in order to provide front haul connectivity to the access points. So we have a different, compared to the first approach, access point topology adaptation in self-free networks. And therefore, we need advanced scenarios to be supported with access points being reassigned to different DUs on demand for the clustering, I mean, based on the traffic, based on the user mobility, etc. This multi-point connectivity, let's say, is supported via beam sharing from multiple access points. And this actually unlocks practical self-free deployments in 6G networks, since it allows them to significantly increase, as we have seen it from the first results of this approach, the spectral efficiency by at least by a factor of 2 at least, since we consider network classification and interference cancellation approaches. And as I mentioned earlier, MARSAL project is aligned with the ORAN Alliance, and we consider in MARSAL that the CU user plane function and the DU are deployed at the radio edge part of our architecture, and the CU control plane and the near real-time rig at the regional edge of our architecture. The self-free high physical layer functions, the modulation, the precoding, are integrated at the DU, at the ODU. Thus, we follow the ORAN splitting option 7.2x. And in this way, we add self-free support in the ORAN architecture, and this is done for the first time. So for this part, for the network design part, the work that has been done in the last period focuses on different innovations. We have methods for combining RU local estimate at the DU that target the signal, the uplink signal detection with the ORAN 7.2x split. We have this project I mentioned earlier, the inter-DU cooperation mechanism that we need for user clustering self-free, focusing both at the uplink and the downlink transmission. There are different approaches for these two directions. We also focus on how to implement approaches for time, phase, and frequency synchronization, this sync plane, by focusing, of course, on the self-based implementation. We have data-driven algorithms for the formation of RU or access point cluster, where we consider different approaches based on the size of the cluster, of the serving cluster, and how this the number of access points can affect that comprise the cluster, can affect the network performance and the load on the E2 interface, because we see this as a bottleneck. We also have machine learning-based trajectory prediction techniques, targeting to update these clustering approaches by considering user mobility. So clusters can be dynamically updated based on how the user moves. We have also working on dynamic adaptability algorithms targeting to define how the self-free network performance depends also on the distribution of the processing tasks, not only on the availability, let's say, of the communication resources. Again, the inter-DU cooperation, we have a lot of work done there and focus on the improvement of spectral efficiency. As I mentioned earlier, the early results, as you can see this in this graph, achieve high spectral efficiency compared to the classical self-free solution. The second solution, radio edge solution of MARSAL, which is related to these large massive MIMO antennas, we have studied the performance of such an approach by considering a testbed provided by our partner Vardakas. And finally, we have this data-driven self-free scheduler that we have implemented for scheduling the resources locally in cases where these access point clusters or RU clusters comprised in a way that these RUs belong to the same to the same DU, sorry. So in this case, we don't need to ask for a scheduling approach or implemented at the near real-time rig, for example, we can do this locally. So for these cases, we can save a lot of time and do this scheduling algorithms implemented at the ODU. Moving away from the user, we have considered the optical transport network in order to provide connectivity to all the use with the mid-haul. To this end, we propose a novel fixed mobile convergence solution in order to facilitate integrated connectivity of both these mobile users and, of course, the fixed users, for example, the FTTH user, fiber to the home users, that share the same mid-haul and edge infrastructure, and of course are both served by the same core. Sorry. So we consider two different transmission approaches, optical-based transmission approaches. One is a standard point-to-point connection, mainly focused on the interconnection of these large antennas, massive MIMO antennas to the mid-haul. And also for the other cases, also in order to provide support to the FTTH users, we have a point-to-multipoint approach based on XGSS passive optical network in order to provide interconnection to all these different serial front-hauling connections of access points, and also, as I mentioned earlier, to the FTTH users. Going to the network management domain and leaving the network design, our work focuses on the development of a network management infrastructure specifically designed for the MARSAL infrastructure. So our work is motivated by the fact that all the previous approaches targeting this optical and wireless convergence at the RAN are centralized. So they cannot be considered as optimal solutions for our network. ORAN is also centralized since the orchestration and automation layer are deployed at the core. So we need to implement a hierarchical control plane solution where we have different SDN controllers for the fixed network, for the fixed users, for the mobile users. That can work under a common orchestration subsystem. And for this reason, we have also defined the interface between these two different controllers that can be used in order to achieve, let's say, load balancing approach between the two segments of the network. So we envision for the network management domain a new paradigm of edge infrastructure. We could have called it virtual elastic infrastructure that targets to integrate all the different resources of the network, the computing, the communication, the networking, and the storage resources in a transparent manner. You can see this approach in the figure where we have different layers. We have the infrastructure layer, which is where we have the communication, the computation, the storage, hardware, over which we assume that this virtual elastic infrastructure operates. We have in the middle the orchestration layer, which is the management hardware and software systems that we are currently developing, and I will show you later more details, in order to control all these different resources. And finally, we have the logic layer that consists of all the different components that are considered in order to analyze monitoring information, perform decision on the scheduling of resources, for the optimization of the infrastructure, utilizing all these the considered orchestration subsystems. So in order to do that, we of course needed to map, let's say, this elastic edge cloud infrastructure into the MARSAL network architecture. This is done by following the architecture framework proposed by EdgeMake and EDV. So we rely on conventional edge-based reference points, but of course updates are needed since we have let's say a special network architecture based on the cell-free approach. So we have already updated several reference points related to ETSI NFV, to the management, to the MEC platform functionality. So we have a new MEC NFV architecture considered in MARSAL. You can see it at the bottom here of the slide, where the blue and the red blocks refer to the MEC and the NFV architectures, where the MARSAL MEC NFV framework leverages the subset of MEC and NFV blocks that are most relevant in order to enable this virtual elastic infrastructure of MARSAL. So we have, let's say, a three-layered network infrastructure architecture with core, regional edge, and radio edge tiers, and our approach focuses on bringing the MEC functionality as close to the UE as possible. This is done by enabling traffic steering between MEC hosts in different tiers, especially, of course, in the radio edge. And the target is to keep the MEC traffic as much close to the edge as possible through horizontal scaling in order to boost responsiveness and also lighten the backhaul traffic. And finally, for the security pillar, we have different innovations in the last year. We are working on the delivery of a decentralized blockchain-based platform that targets to support network slicing transactions through the consideration of smart contracts. And this platform is integrated with a network slicing as a service subsystem. We have this is realized through the development of data anonymization techniques that can allow the common solving of complex machine learning tasks without the need of sharing the raw data with competing partners. Since we are in a multi-tenant environment, these competing partners refer to the other tenants of the infrastructure. We have also developed a smart contract platform that, in order to negotiate the resources of a network and allocate them to the MVNO as needed, of course, and this should be done in a timely and efficient manner. And we have also worked on the policy-driven collaborative computations, where we target to provide security and privacy, able to guarantee data information security in such a multi-tenant environment. And different algorithms have been developed so far for this approach. And finally, we have worked on the delivery of machine learning assisted hardware accelerated slicing security mechanism. This is implemented by considering by focusing on infrastructure that supports security solutions that belong to the domain of machine learning. So we used, in order to do that, we use an external computation source, for example, a GPU, and this GPU will expect a user-defined input. And for this reason, we need an advanced telemetry system. We also work on the protection of the users against malware and other attacks from the networks. And finally, we have investigated the way that the availability of high-performance networks can help, like the case of MARSAL, can help in the development of efficient data anonymization solution for the cases of massive amount of data through the distribution of these different tasks to different nodes of the network, and apply this approach in this multi-tier network infrastructure of MARSAL. So this is the work that has been done in the last year under the framework of MARSAL. This is the fact sheet. we have started the work of year 3. We have provided the deliverables, the final deliverables of the technical work packages a few 3 months ago, and the final specification of the network architecture a few weeks ago at the end of the year. And we are looking forward for the next phase, which is the proof of concept phase, where we have defined 4 different scenarios, and we have already started working on the implementation of these experimental scenarios. So thank you very much. If you have any questions.
There is a question in the chat already for you.
Let me check. We need to move more functionality from your. Yes. There is a challenge here, and we are currently working on different algorithms in order to check how we can solve this approach. We have seen the problem of latency. This work has been done by KUL, our partner, KU Leuven, the University of Leuven, but we also from eQuadrat, we are working on algorithms that target to study the functionality to study how we can, by moving functionality from the antennas, from the access points to the DU, can affect not only latency, but also the utilization of the resources at the front hall. So we believe that we can have an answer in the next period of time, probably 2 or 3 months, in the next series of deliverables of MARSAL, which are in March 30, I mean, end of May or end of or June. But yes, we have seen this issue.
Thank you, John. We are slightly over time with the presentation, so I would propose that we move forward. Okay. And next one would be the Bjoern 5G Open project. And Oscar, please.
Okay, I hope you can hear me now.
Yes.
Now let me share the screen now.
Yes.
Okay,
Slides can also be seen.
Perfect. So we have, I guess, some time also for we should allow some time for questions, right?
Yeah, yes. So the 20 minutes of presentation time includes a couple of minutes for questions, and currently we are okay with the time.
Okay. So first of all, thank you for the invitation to participate in the workshop. So our project B5G Open is one of the few ones that are really dealing with the lower layers of the network, and we wanted to present you today our vision on the end-to-end for the optical networks ready for beyond 5G services. Okay, so we are gonna show you which is the view that we have. First, what are the use cases that we are trying to solve, and this is why we are preparing this really high capacity network. What are the key features that we are gonna develop within the project that we are developing, and present you this high level network architecture, and a little bit of the technologies that we are touching, and a little bit of the control plane architecture. I won't devote too much time on the control plane. It devotes itself a whole presentation on that. Also not in detail in the technologies that we are working in and prototyping. Okay, we are work in progress. So what is the motivation? So we are seeing that all the 6G and or beyond 5G services that are being proposed are pushing the limits of the networks that we have today. So we have been studying the use cases that are being proposed, and we have selected those that we consider more relevant, like the quality of communication, the high precision communications, or the holographic teleports. So with the network that we proposed that should be for the next, let's say, 10 years or so time period, 2025, 2030, should enable these low latency services and allow transmission of different videos, including hologram transmission. So then we want to minimize as much as possible the latency in our network, so you have budget to do whatever processing you need to have. So we are working in a network architecture that we are basically working in optical technologies in the different segments that we will see, and also combined or joint packet optical solutions with point to multipoint and point to point transmissions. Okay, so also we have selected here a number of use cases that could be enabled here. For example, we can enable also the digital twins, the industrial IoT, the traffic internet and remote operations, and holographic telecommunications. All of this we have analyzed to support. So what are the features that we will have? As mentioned, the use cases that we have been analyzing require the capacity and latency and even availability, okay, not only capacity and latency, to the next level. Okay, so that means we need to redesign our networks, and just a summary of a hint on the future. So first of all, we focus on having a multi-band operation. Okay, so right now we are working with mainly with the C-band. In some few cases, okay, today there are some, but very, very few deployments today that are extending to L-band, and we see that extending to the OE and S bands can increase up to 10 times the available capacity. Okay, so we could cope with the requirements. We will see later on that we don't need one of the when we have been studying where to deploy this capacity, we don't need to have the full network multi-band. Okay, so it's important to understand that one of the requirements that we have found is that we can enable and start adding selected bands and different parts of the network. So some of these bands, okay, the problem that they have is that the losses are higher. They are not in the main transmissions window that we have been using. So, but that doesn't mean they are not usable. Okay. So today in the C-band we can reach even to even more than 2,000 kilometers. Okay. So in the other bands, I mean, if you can, if the range is shorter, there is no issue. For example, for an access or for a regional segments. Okay. So we envision that we can have, for example, slices with this band. Another important concept that we have is the optical continuum. And by optical continuum, I am not referring to have that everything is full optical. Okay, we will see that the requirements in the different parts of the network will be different, but that does not mean that even if we have different segments and even different suppliers, that does not mean that this is a barrier. Okay, like it's today. Now today, every segment you need to go out of the optical, full optical. You need even to sometimes to go to the IP/MPLS layer and then go back to the optical. So that imposes or that takes out some latency budget, also cost, power. So our vision is to break those barriers and to be able to do connections regardless the segment where the connection is, or the endpoints of the connection are located. Then also in our project, we are also dealing with access technologies. Okay, so we're mainly working with PON and Li-Fi technologies, the two optical like access, and we foresee that the access should be integrated, at least from the control perspective. And we will see in some cases we could even extend the range of the access. But we need to work it seamlessly with the network. And for the control, we envision to have two main control. One is the end-to-end network orchestration, where we also take into account the capabilities, the computing capabilities that we can locate in the different nodes of the network, and also working this autonomous network operation. So the intention there is to have as much as possible an intent-based approach. Okay, don't avoid going to the low level and having to or allowing these zero-touch networking paradigms. So we are in our architecture, we are relying on this streaming telemetry where we learn what is happening in the network, and we are providing engines and computing capabilities and models that mimic the behavior of the optical network, and we can know in advance what is happening. So in the architecture, I show you what would be how we have a structure, how a national operator network would look like. Okay, here we have focused on countrywide networks. Okay, so we have divided in the access, what we consider the access part that goes from the access central office, that is the building of the network operator that is closer to the user. In the middle, you could have some street cabinets, and then you will have the access points located in the at homes or at the radio stations. We have this metro aggregation and metro core part, which is more in the regional wide scope, between 100 and up till 300 kilometers, and then the backbone. So we have deeply analyzed every of these segments, and the characteristics of them are really different. Okay, so even we wanted to make a full end-to-end interconnection. It's really impossible to to do it always. Okay, and even if it's impossible to have the same technology for all the segments. Take into account that most of the connectivity requirements tend to stay in that network segment. Okay, so we have some cases where we can expand services, but in most cases they remain in their segment, and we see that each one would have some sort of different topologies. For example, in the metro aggregation, we have what we call the horse shows, that are 2 points and collecting traffic from different ones, resembling the shape of a horse show, or rings. And in the metro core backbone, we have the more mesh topologies. Also, we have the numbers and size of the central offices is much higher in the access rather than in the center. So depending if we are more in the edge or more in the backbone, the requirement, for example, in terms of cost and power would vary. Okay, towards more the access, we will require, or these requirements in terms of cost and power will be more stringent. Okay, while in the more core, we could handle some more. So here in the project, and then you have this available in the public deliverables that we have made a compilation with 3 network operators, with Telecom Italia, Telefonica, and British Telecom, taking into comparing our foreseen architecture and the number of nodes that we can have in each of them. Okay, and the number of central offices that we can have in each of these segment access. Okay, so and you can see we even network operators, we use a little different terminologies, and we came different backgrounds. In the end, we could manage to have, let's say, more or less an agreement in the terminology and in the numbers. We are more or less agreement. So we have in this area of the access more than even the cabinets even can be in the order of thousands. For example, in aggregation nodes, we have in the order of tens of thousands. Telecom Italia also in the order of 20,000. So you see, more or less, the numbers are appropriate. So in the project, what we are doing is identifying which is the technology that is best suited for each domain, and also following the principle of optical continuum, allow this interconnection of them. So what are the requirements that we are putting to these technologies? So first of all, we foresee that it is required to have a tight integration between the packet nodes. Okay, we reckon that the traffic today is shared mainly by IP MPLS routers. Okay, and sometimes also layer 2, but more in the data center. So what we require is to start directly the optical connection from those devices. Okay, so let's try to avoid having the traditional architecture that the packet device or the switch or the PON device or whatever device has a client and then goes to a transmission box and then into the optical network. So integrate directly the pluggable in the so we have a whole activity in the project dedicated to investigating the packet optical integration. We have prototypes. We have a lot of work in the control plane, and we are working also with both suppliers of the technology. We have in the project Infinera. We have also Nokia, ADVA. So we have people working in those parts, and we are integrating them in the project to prototype in white boxes. Okay, but as a generic architecture, we foresee in the future that this will be applied not only to white boxes but to all others. Also, another key concept that we need to have is the partial optical disaggregation. Okay, so it is mandatory that we have open line systems that can support what we call the any coherent lambda. So any coherent transmission should be able to pass through the line systems. Also, the multiband, we mentioned at the beginning that it was one of the key concepts, but the requirement is that it can be gradually activated, even sometimes in a link-by-link basis. Okay, we have seen that just by activating these extra bands in some places can enhance the capacity a lot. And as mentioned, in order to avoid this walling of segments, have a transparent interconnection in domains, and continue with the drop and continue functionality in the access node. So here, this is how we foresee a little bit each of the segments. So, for example, in the access part, we foresee that we will have a diverse landscape. So we can have WDM in the access to allow all the functional splits and to be able to increase the capacity there. But also we will have these TDM PONs combined. Even sometimes with the TDM PON, we could even go further, and many of the central offices could be redundant. Okay, but we see that it is there is a reason to still end these connections at the local CO, especially for the processing capacities. So you have its functions, you could terminate there. But also we foresee that there could be cases where you could go directly to the regional central offices. And here we are working with some technologies, for example, the XR technology, to be able to deliver high capacity connection in point-to-multipoint structures. Also, we are working in Li-Fi use cases, which is an enabler. Delivers connectivity of up to 50 megabit now, foreseen to increase with optical. So we can have users that are moved and are covered by the Wi-Fi connection. So one of the technologies, this is one of the technologies that we are exploring. In the metro aggregation segment, we are looking at which are the technologies that we require, and here we focus mainly on having in the switches. We are okay with the 2-degree switches, but we can have a smooth upgrade to 4-degree to be able to increase the capacity. And also, we require to have the possibility to manage both the point-to-point and the point-to-multipoint channels. We mentioned that one of the technologies that we are exploring is this point-to-multipoint that can save a lot of fibers. And in terms of multiband, we see that the C extended C and C+L should be more than enough, okay? But we see that in some cases we can go to O-band and we can have, for example, some slices of O-band for the local traffic. So this is a way easily to perform physical slicing going to the band. And this is the architecture that we are building for the central office and the cloud central office and the regional central office, in which we are incorporating the packet optical node and the multiband optics. So this we are working on it. We have some work on it in our deliverables, and in recent work, in future work, you will show the prototypes available. If we move to the backbone, there the capacity requirements, and we are aggregating all the traffic is much higher. Yes.
Just that, how is it with your timing? So
I just gonna finish.
Okay,
yes,
great.
I just gonna finish with this, just with the backbone. We are we are at the end of the backbone. So here we want to increase the capacity up to 270 terabit per second per link. Okay, so here we are extending, even including the A+O bands, and a smooth upgrade periodic to reach all the bands. And we want to include their coherent interfaces with increased spectral efficiency, so to have more capacity. And in the long term, we see that we need to go also to special division multiplexing. So even multiple fiber, we are envisioning not to change the fiber. Okay, so multiple parallel fibers, for example, we see that it is the foreseen in the future, and that we should allow the coherent lambda. So for the control architecture, we see that on top of this, we will require a set of controllers. I will not enter into this detail, but we are working in a prototype of the control of this architecture with the packet optical node and the multiband node. So here can just conclusion that we have presented this high-level view of the architecture with the different segments, different requirements in each of them, and transparent interconnection to be able to perform this optical continuum. Key features: multiband, IP optical, and an SDN-enabled control plane to be able to manage all this capacity. And to know more, visit our page and you will find our first public deliverables. And so, questions?
Thank you, Oscar. In the chat, there is not immediately any questions, so let's see if there is appearing or anybody else. Now there is a question. Although it's for MARSAL, so I don't know if it is for you or for the previous project, but
which is the question in
the question in the chat currently is: have you done the calculations to show MARSAL delivers enough bandwidth? Maybe you can apply it for your project.
Yeah, I mean, because we have done this would be more for MARSAL, but here what we can what we can do from our side, from the network, is to we have made the calculations of the bandwidth required for the for the proposed 6 use cases. So if some project has some specific requirements, okay, please bring it to us so we can ensure that we can provide the necessary bandwidth. Okay, so take into account the technologies that we are envisioning here. I think we have in mind the big requirements, very stringent requirements in terms of bandwidth. Okay, but and the calculation that we did it were mainly for a set of we analyzed a set of 5 beyond 5 use cases to make those calculations, at least in our case.
Yeah, thank you, Oscar. And then to have the proper time also for the last presentation, I would propose to move to that. So it would then be the RISE 6C project, and it would be Vincenzo, please. So we have with the RISE project the problem with the participation.
I'm here. Can you hear me now?
Yes.
Okay, sorry, I couldn't unmute myself. Give me 1 second, just trying to share the slide, and then I will also activate my camera. Can you just give me 1 second, because I think I need to restart the application, say that I needs to be updated in order to share the presentation. Give me just 1 second.
Yes.
Yeah. Okay. Now it's gonna work. Can you see it?
Yes, we can see the slides and I can hear you.
Okay, now let me also activate my camera, and then it should be fine. Okay, I think now you can see me, right?
We can see you, but unfortunately, I think we lost the slides.
Give me 1 second, sorry. Now, can you see it?
Now everything fine.
Okay, so I think we can start. So, sorry for this delay. Thanks a lot for this opportunity. Good morning. I'm Vincenzo Sciancalepore from NEC Europe Lab, and the principal researcher, and also, let's say, the project technical manager for the RISE 6G project. Basically, today I'm gonna give you this very brief presentation on this RISE network architecture, and about some deployment strategy that we have been analyzed, and also, let's say, providing and building within our project activities. So if you have, of course, any further question, comment, or even some, let's say, offline question, you can just drop me an email. Here you can see my email address. So let's start. Basically, let's say the rollout phase of the new 5G standard recently started, as you might know, and we can experience unprecedented communication and localization performance as end users. So basically, let's say we should start balancing benefit of such new technology against cost and of course drawbacks. 5G and beyond 5G base station will exhibit unsustainable hardware cost, and let's say novel introduced transmission solution will be highly complex and entire power hungry. And finally, let's say the high frequency band expected will directly influence on the propagation properties, as the material penetration will be impaired, thereby resulting in a, I would say, huge base station densification process. This means that we need a new technology in order to, let's say, address all those drawbacks and in order to push the, let's say, the overall network architecture toward what we call now 6th generation of wireless networks. The answer could be, or let's say in our case, is smart surface. Smart surface is, as you can see here, a fixed flat surface with an array of antennas that we call reflectors, and an RF switch is to configure phase shift per antenna, and a controller computing wave mechanisms for changing the reflection angle. This, let's say, very basic. This is our very first prototype of RIS, as you can see here, that we have also been, let's say, building and proposing within the project, but I have another slide later. And let's say, you can see here how this may work. So basically, we are just proposing a very nearly passive device, as you can see here, with, in this case, 100 antenna elements that can be dynamically controlled in order to change the reflection angle of the impinging wave to a specific direction. And this, of course, would open up to a huge number of business cases. I just, let's say, summarize here the, let's say, the effort toward this specific new and emerging topic called reconfigurable intelligent surfaces from the main government funding agencies from US and also Europe. As you can see here, Europe is, let's say, going very far toward this topic. As you know, the investment is quite huge in comparison with the one provided by NSF and by US. And there is also, since now it's more than 1 year, a new ISG standardization group, a European standardization group from ETSI, that is called the RIS. Basically, this ETSI RIS is running, as I said, since September 2021, with 3 work items, main work items, one on use cases and deployment scenarios, one on the, let's say, impact on the architecture and standards, and the third one on the communication models and channel models. Those documents are going to be released in this month. So next month will be the final version will be public, so you can even have a look. But you know, this is just to, let's say, state that Europe is moving ahead toward this specific topic, and they see a lot of potential behind that. Now let's go into the, let's say, some details, some definition of the concept. What is, let's say, the reconfigurable intelligent surface? Basically, the definition says that RIS or RISs are man-made nearly passive surfaces of electromagnetic material that are electronically controlled. This means that, as you can see from this picture on the right side of the slide, this is the classical material. That could be a kind of random scatter. So you have the incident wave, the impinging wave, and then you have the reflection wave following the Snell's law, the physical, the very well-known Snell's law. We go beyond that. With the smart surface, we can control, for instance, some of the propagation properties. So we started very simple, just controlling the reflection angle, as you can see from this picture. So this is, again, the same incident wave or impinging wave. And then we can control how we can reflect, or how the surface, the material can reflect this specific wave. So for us, the RIS will be, or is already, a new type of system node where, let's say, the response can be adapted to the status of the propagation environment, which means that now we are posing the control on the propagation environment itself. This is also the reason why we call it smart radio environment, because now we can see the propagation environment no longer as a black box, but we can get the control, the full control of the propagation environment by installing a huge number, let's say, a number of smart surfaces around. Smart surfaces are supposed to be low cost, low complex, nearly passive, as I just said. So this, let's say, would also help a lot while deploying a huge number of smart surfaces around within the propagation environment. But now the main challenge, the main technical challenge would be how to design and control reconfigurable intelligent surfaces while enhancing network communication and also localization capabilities. Let me check the time. Okay. This is just a very brief introduction overview about the project, the RISE-CG project, since the RISE-CG project is fully focusing on this emerging topic. So the vision will be just to have this RIS technology to achieve intelligent, sustainable, and dynamically programmable wireless environment, as I just said, in order to push this new concept of smart radio and propagation environment. And the expectation is that RISE-CG project can actively, as is already done, doing, in the main standardization bodies on this specific topic. And of course, is, as I said at the beginning, Europe, let's say, is very keen to get the leadership of this new technology. This, let's say, will secure a kind of European technology leadership, supporting the creation of new services oriented to this, let's say, topic in the beyond 5G and also in the 6G global race. We do this, let's say, within the project from a theoretical perspective and also from a practical perspective, as we will see in the next slide. This is the consortium overview. We have the coordinator, which is CA in France. We have the project technical manager, is myself and NEC Europe Lab. And we have, let's say, the innovation manager, which is Stellantis, so let's say Fiat in Italy, as one of the two main verticals we have in the project. What do we expect after this project and after this technology, let's say, will get mature? Basically, the idea would be something like this nice picture. We can get RIS around. We can densify our propagation environment without putting active devices, which means costly devices, which means maintenance, which means CapEx and OpEx. But we can install low cost, so inexpensive, nearly passive devices around in order to push for new business opportunities and new business scenarios, as you can see in this nice picture. So we can have something like in a, let's say, some dense scenario, like in a train station. We can have outdoor to improve the communication capabilities. We can have in Industry 4.0 to improve the localization accuracy, as you can see in the next slide. So basically, I can just skip this, but the idea would be from the RISE-CG project to get an only one architecture and to get some, let's say, initial prototype that will be used to demonstrate that the technology is ready and that we can use it to get new system and network performances. This is the first, as I said, this is how we tackle the problem from the practical perspective. So basically, those are the ones that have been pushed so far from different project partners. So those are the first prototypes of the RIS, so what I call the available RIS equipment, targeting different frequencies, because of course, different frequency may require different technology and may, let's say, get into different requirements as frequency, as, let's say, resolution, as cost, and so on. As you can see here, we have a pin-diode technology for the RIS built by CA. We have a Greenweaver company, which is a, let's say, a startup or an SME just focusing its business on RIS with this pin-diode working at 27 gigahertz. We have the NEC first prototype of the RIS based on the RF switch technology working at 5.3 gigahertz, and so on. But let's say the idea would be to cover, after this 3 years project, all the bands. So the S band, the KA band, the V band, the D band with a working prototype. You can see, let's say, you can find more details within these deliverables that have been released by the RISE-CG project. Now let's go into some, let's say, more theoretical details and practical use cases. This is one of the, let's say, case study that we have been observing and evaluating within last year. This is the Rennes train station. So the train station located in Rennes in France, that will be one of our field trials at the end of the project. Basically, the idea would be to get this train station scenario, as you can see here on the top right side, where orange have 2 deployed base stations. Basically, let's say they argue that there might be some communication dead zone where the coverage is very limited due to the topology and of course the obstacle and the scatters placed within this scenario, as you can see from this dark blue zone. So the question would be, can we just exploit this new emerging technology to improve this situation, so to solve the communication dead zone problem while installing an RIS without installing an additional base station, so keeping the cost, the installation cost, the maintenance cost affordable? And the question is yes, at least from our first analysis, as you can see here. So we just, let's say, deployed a solution, an algorithm to optimally place RIS within this scenario. This RIS, let's say, doesn't really need to get a communication with the base station, but this is something that I will show you later. But basically, the idea would be just to install, as you can see here, 5 different RIS within that scenario in order to alleviate this communication dead zone problem. And this is exactly what we've done with our ray tracing using MATLAB, and those are the results, as you can see here. Just compare, let's say, against the random placement model. So this, let's say, of course, is a kind of motivation for our activities and for our technology, because this means that you can achieve better performance without installing additional active base station. So keeping the cost for the operator in this case very low. And then, of course, the main question would be, how much is the gain in terms of cost, CapEx and OpEx while installing RIS instead of active base station? This is a kind of analysis we are currently carrying out within the RISE-G project. Hopefully this will be ready by the end of this year and the end of the project. But basically the idea is that, with additional nearly passive, low cost, inexpensive devices like the RIS, we can achieve very good performances rather than just installing active base station. And then this would be the second field trial within the project at Fiat premises, as I introduced at the beginning of this presentation. So for the Industry 4.0, where, let's say, the localization accuracy is also something of paramount importance, because in that case we can use, for instance, in this specific scenario, 2 different RIS, again nearly passive RIS devices, in order to, let's say, get a more accurate information of the position of a specific target. So the idea would be to use some existing network infrastructure. In this case, we have this 5G base station provided by TIM, Telecom Italia, in Italy, within this specific, let's say, scenario environment. Basically, they can use the existing infrastructure to provide an additional service. In this case, the service would be the localization. In this case, we can install additional RIS to improve the accuracy of the localization. And then we can use, like you can see from the slide, millimeter wave based communication at 27 gigahertz coming from this 5G base station in order to localize a specific AGV, which is this robot here, within an area of 5 by 5 meters squared. Now, getting, let's say, into the core idea or core part of this presentation, how can we really integrate such new devices, such, let's say, novel and emerging equipment within the existing network architecture? And this picture, which is the first one we provided a couple of years ago, provides a kind of, let's say, example how we can really get into this very big picture. Basically, here you can see a kind of ORAN compliant architecture on the right side, this in blue, with all the ORAN reference point. And here you can see how we, let's say, envision the RISE device and the RISE controller directly interacting with, for instance, the near real-time controller coming from ORAN. Because basically, just
a reminder on paying attention on the time. So we are up very near the scheduled ending time. So how is it?
Get 5 minutes more?
I mean, from my point of view, you can talk 5 minutes more, and then it depends on the audience if they stay online or not, because there is no other presentation after you.
Okay, I mean, I need just 5 minutes to close this, and then we can get 1 or 2 questions if you want. Okay,
I find it very interesting if you could continue. Thank you.
Thanks a lot. So basically, let's say this is what we envision at the beginning of the project, how we can interact with this RISE or RIS or IC controller and the near real-time controller provided by Bjoern, because basically we need the kind of interaction between the base station and the RIS device, because the base station the active base station needs to decide the beamforming, so how to configure the beamforming towards specific direction, and at the same time, someone needs to configure to control the RIS device in order to reflect the impinging wave coming from the base station towards specific direction for specific, let's say, objectives. So this kind of interaction is what we call the joint optimization of base station and RIS. That, let's say, we also done some theoretical algorithm and activities on this, but I didn't put it because it was, let's say, a bit out of scope, can be realized within this interface. So we need a kind of new novel interface among those guys, among those entities, in order to exchange information and decide how to actively configure the base station and passively configure the RIS. And then, of course, this can be done at different time granularity, depends a lot on, let's say, the requirements, but can be also done within the service management and orchestration layer. And this is something that, let's say, we recently put in one of our latest deliverable, as you can see here on the bottom side. Basically, the idea would be to expand this kind of RISE architecture, get what we call RIS orchestrator. As you can imagine, this can work at different time granularity, about a few seconds. We can get what we call RIS controller, which is the one directly talking to, for instance, the near real-time RIC. So we can imagine a kind of peer-to-peer interaction among those two X apps. One here that I, let's say, personally called BS-RIS joint optimization, but of course we can change the name. And the other on the other side, we can have a direct interaction in order to control the base station again and the RIS controller. And then we have the real RIS control plane, which is the one changing, the one triggering the current RIS configuration. And we can even think about this kind of, let's say, 3GPP compliant interface. Of course, all things that you can see here are not standardized, but we, let's say, are trying to provide kind of model and data model for these new interfaces. And this can be a kind of F1 interface like the one we have for the C plane and the U plane, but just adapted to this specific interaction. Basically, this can talk directly with the CU control plane. But of course, again, this is just our first result, first achievement that we are currently evolving. So no one prevents us from getting a direct interface between the RIS control plane and the DO here. Okay, since, let's say, I don't have too much time, I will just close this presentation with this final part. When we get, let's say, what we call self-configuring RIS, because an additional or a different scenario could be in what we have seen so far is that we need an RIS deployed with this scenario, and the RIS needs to talk directly to the base station in order to be jointly optimized. But we've also built a different kind of RIS that we call self-configuring RIS, where let's say a customer can go to some electronic shop, buy it, install it wherever he wants, and then the RIS is able to automatically detect where is the base station and where are the users and self-configure itself. And this would be the main novelty behind what we call MARISA, this, let's say, new architecture and solution. In this case, of course, you don't need to integrate this within the existing network architecture, but you can have those self-configuring and hopefully even energy autonomously RIS around, even in your place, indoor, outdoor, as you like. And then once you activate this self-configuring RIS, the device is able to automatically detect the active or let's say the ongoing communication and improve your specific network performances. This is how we have done this. Of course, this is no longer a nearly passive RIS, because for this specific part, we need some, let's say, very limited sensing capabilities on the RIS. So cannot be anymore a passive device, but it's a passive device with some limited sensing capabilities that introduces, let's say, partially some active components within the circuit design, but still the RIS is consuming very limited energy and can provide, let's say, very interesting performances. If you let's say you are interested in this kind of new approach, I would just suggest to refer to this paper that has been published last year. And as I said, we are now evolving this into a real prototype where we can really validate whether this self-configuring list can be a viable solution. Okay, just to, let's say, conclude, basically the takeaway message today would be four main keywords. Openness, because the smart devices can be freely installed and configured, as we have seen. Fully passive or nearly fully passive devices, no need for active radio elements or components within the circuit design. Limited cost, as I said, inexpensive devices, as the electronic printing costs are kept affordable, and a smaller carbon footprint, as the passive elements will require only energy for the control circuit. Okay, sorry for being a bit late. If you have any question, as I said, or if you want to send me an email with your offline comments, feel free to do it. I will be glad to take all your comments. Thank you.
Thank you, Vincenzo. There is actually several questions in the chat already. So if the audience wants to stay online, you can also comment them verbally here, or you can also.
Yeah, I'm just trying to see whether I can see this without, let's say, losing the sharing of my screen. Just trying to find it. Oh, okay.
If you press in the upper part, you press chat, and you can also stop sharing if that's easier for you.
Okay. 100%. Good, I'm here. Okay, so let me just I'll just start from the beginning. Actually, we have seen the mathematical model for traffic management in our architecture, and we have just informed that, okay. Not sure whether this, okay, Vincenzo, very interesting. Simple question. Do I get it right that the RIS equipment is not gonna to replace active message, but to complement it? Exactly. So the idea would not be to, let's say, change the existing deployment. We cannot do that because, you know, network operator have invested a lot. But the idea would be to complement it with affordable cost. So the idea would be to use the existing network deployment and architecture, and additionally install RIS devices to improve the communication capabilities, and as you have seen today, also the localization accuracy. Just installing additional RIS devices into the existing network deployment. Here's the concept behind the RIS equipment towards COTS hardware, and or the expectation is that each vendor will have their own RIS variants. Basically, the main, as we also, let's say, now are quite expert on the RIS, let's say, prototype and building RIS. Basically, changing the frequency will change the RIS, let's say, design, the layout design, because of the interdistance among the antenna elements and so on. So it may happen that we have also been working a bit on this. We have, let's say, designed what we call the multi-frequency RIS, which is a kind of RIS able to change the operating frequency by, let's say, virtually change the interdistance among the elements. But basically, each operator has its own license, which means that each operator will need its own RIS device and RIS design. This means that probably the operator will buy it for a specific operating frequency, and then will use it. We are also trying to push for a kind of RIS provider, which is the one probably owning a kind of RIS infrastructure. And then we are trying to, let's say, see whether it might happen that the RIS provider is able to share its infrastructure among different operators. But as I said, this also requires different RIS design based on the operating frequency. And since each operator has a different operating frequency, this might be a bit problematic. Yes, very simple questions. In current or envisioned solution, with what angular granularity can be reflection and control? It's near continuous. So it's of course a discrete steps, because in our specific prototype, we are using 3 bits. 3 bits means that we can get up to 8 different phase shift states, but one of those is used to get the absorption state, which means that now at the end we have only 7 different phase shifts to apply to each of those antenna elements. So, but honestly, we have tested with 2 bits, 3 bits, and the difference is not too much, because of course, the main problem there would be the size of the RIS, the frequency that you are using. If you are going for sub-6 gigahertz or for millimeter wave, it will change a lot. But of course, let's say getting a more complex design will help you to get, let's say, much more possibilities and options for the reflection. But this would go against the low complex or low complexity feature that we are claiming for the RIS. Can an RIS be turned in a real time to have a reflection follow a moving usage? Yes, this can be done. In our specific prototype, we can change the configuration. I mean, this is just the first prototype, and we can change it around 30 milliseconds, the configuration of the RIS. But with some advanced technique, you can even change the RIS configuration every few milliseconds, which means that with let's say, a proper controller, you can even follow, let's say, UE or user moving. How large do you foresee an RIS can be in the practical 6G deployments? Could this cover hundreds of square meters? Or this depends again a lot on the sites. So indoor would be, let's say, an easier case. Going for outdoor scenarios means that you need also, depending on the frequency, a quite, let's say, large RIS, what they usually call holographic RIS. So what we expect to do within the next months and the next years is to have a kind of modular RIS. So you can place together multiple RIS. In our case, the RIS I've just shown you is 30 by 30 centimeters. So it's not so big, but we have already 100 elements working at 5.3 gigahertz. If you put multiple RIS together, of course, you will get a larger RIS, and you may even, let's say, get better performance in outdoor scenarios. The main problem is that going towards higher frequencies values, like millimeter wave, means that the size is going to be reduced a lot. So within, for instance, 10 centimeters by 10 centimeters, you can even get 1,000 antenna elements, which means that for, let's say, reasonably big or large RIS working at a millimeter wave, you may end up with 1,000 and 1,000 antenna elements to control. And this might be again against the, let's say, the low complexity paradigm we have been talking before. In the presentation, I see the reflection rate, but where is the intelligence? Actually, the intelligence can be in this block that I called the RIC controller, can be on the ORAN side in case we have this kind of interaction and interface between the RIC and the RIS controller. But of course, the RIS device itself should not have any intelligence, because again, this is designed to be low complex device. What frequency was planned to be used on the RAN station trial? Those are 5G conventional 5G base stations, and basically they are using, I think, the frequency. The license for Orange in France is around 27, 28 gigahertz. So the RIS will be using the millimeter wave band around 27 or 28 gigahertz. I think yes, I covered all the questions and comments. If you have additional questions, just send me an email. I would be glad to.
Maybe just ask a question here regarding the comparison with other type of technologies. If there are any kind of like analysis for cost benefit of risk compared to, let's say, active solutions like femtocell or something like that. If you can comment on this.
Yes, we added, I think I mentioned, we didn't have so far a real economic analysis because this was not planned within the project. But this is something that we are doing because this would be one of the probably main motivation behind the risk technology. Just let's say this very simple example in RAN scenario where you can just compare 4 or 5 RIS installed there. Let's say in my experience with our prototype, we could build it with less than 1,000 euro. This means that probably going towards mass production, you will get an RIS devices perhaps with 100 or 200 euros or dollars. This means that if you can place there 5 RIS, spending probably 1,000, 2,000 euros, and you can get affordable, let's say, reasonable performance, comparing to installing a new base station, new active 5G base station, I guess the gain will be, let's say, very high. But this is a kind of, let's say, 2 seconds analysis that I can, let's say, do it now. We are trying to carry out a kind of more intensive and deep analysis on the economic and business case. But I mean, this is at least from my experience what I can tell you.
Yeah, thank you.
Yeah, thank you, Vincenzo, for extensive replies as well as the presentation. And thanks everybody for presenting today, for participating, for being active. And now then, yeah, we are a bit over time and also end of the agenda. So time to close the meeting today and see you in 1 hour 45 minutes for the last session of this 2-day workshop. So enjoy your lunch or whatever break you are planning to have.
Thank you.
Thank you. Bye-bye.
Thank you.